Okay, so good. Actually, it's evening. I was going to say good morning or even good afternoon, but long day, lots of stuff going on. So, anyway, here we are with our video. We're going to do inverse trig functions today. We've talked about inverse functions before, but never inverse trig functions. So, I want to start you off with something that you totally already know about, obviously, which is 5 squared is 25. We all know that nice little factoid there. But if we didn't know that, and we had this equation here, and we ask ourselves, well, what number times itself makes 25? How would we go about figuring this out? Is there some sort of method, some sort of mathematical thing that we can do to this to make it so that we can get to our answer? And the answer, of course, is yes. We can take the square root of both sides. And I know this doesn't look like anything like trig, and that's fine. We just need to talk about this little thing first, just to kind of set the ground rules here. And of course, we always want to do plus and minus when we do that. And so we end up with x equals plus and minus 5. Okay, but I want to go back to this bit right here. This is the important part. The way that we were able to get x by itself here is we took the square root of x. And of course, if I were to ask you what's the relationship between squaring and square rooting, you would say that they are inverses of each other. And so we're going to apply this concept of inverse that we already know something about in terms of polynomials. We're going to do that with trig functions. So let's again start off with a fact that we all should know, and I saw that some of you at least already practiced on thatquiz.org working on your trig function values. So we should know that the sine of 30 degrees is 1/2. That's one of those that's kind of the easiest one to memorize. And so likewise, we should be able to have a notation for this. The sine of some angle is 1/2. What's the angle? Just like we had up here. Some number squared or multiplied by itself is 25. What's the number? Same thing here. So what we need then is a function that's going to be an inverse function. So what we really need here is we need an inverse sine function. And what notation did we use from back in the day for inverses? And hopefully you all remember that notation was after the -1. I'm going to put that right over here. So the -1 exponent indicates our inverse situation. So if we want to talk about an inverse function, we have after the -1 of x. That's the way we indicate an inverse. So we're going to do the exact same thing here. So the inverse of the sine function is that, raised to the -1 power. So sine to the -1 means inverse sine. Obviously, cosine to the -1 is inverse cosine, tan to the -1, and so on are all inverses. And we have a second way of notating this, and that is y equals arc sine of x. It's the same thing. Different notation, it means the exact same thing. And all it's asking here is what angle, arc angle, what angle has a sine with this particular measure right here? Same thing here. What angle has a sine with this particular measure right here, or this value? So, time to get out your calculators. And, crap, I forgot my calculator downstairs. I don't want to pause the video. So we'll just make some stuff up. Oh, wait a second, I have my phone. Whoosh. Okay, so this one's easy enough here, obviously. So sine -1.5, I'll show you that on my calculator right here on my phone, but I would have a graphing calculator. There we are. Okay, so on my phone we have, oh crap, I hope they have a second sine. Yeah, they do. Okay, good. All right, so we're going to do, and I haven't done this on my phone, so I may get this wrong the first time in terms of order. So I want to do second sine, there it is, sine -1, second sine of 0.5 equals, and that's 30 degrees, which is exactly what it should be, of course. So inverse sine of 0.5 asks the question, what angle has a sine that's 0.5? If we go all the way back up to here, 30 has a sine that is 1/2 or 0.5. So this just asks the question in a convenient way. What angle has a sine that's 0.5? And so from the calculator, we get 30 degrees. So of course, just make sure you're setting your calculator in degrees when we're doing this sort of thing. And obviously it also works with radians, but for the moment, we're just going to do degrees just to make your lives less painful. Okay, so let's do another one of these. Let's do cosine -1 of, let's say, 0.92. Now, of course, we all know that the sine, or the cosine and the sine, both have a range that goes from -1 to +1. And, is this getting darker? Oh, there we go. We know that the cosine and the sine have a range that goes from -1 to +1. So the number in here for these two functions has to be somewhere between -1 and +1, because this is the function value here. Okay, so we're going to do what we just talked about. So we're going to do inverse cosine of 0.92. And, oh, I did not want to do times. All right, let's clear that. So inverse cosine of 0.92. And we have 23.07 degrees. 23.07 degrees. So again, just using your calculator to do this. We're just going to do sine, cosine, and tangent today. We'll do secant, cosecant, and cotangent next time. And let's do tan -1. Now, of course, with a tangent function, we know that because of the nature of the tangent function, which I'll make a little quick sketch right here, we know that the tangent function does this. So y values can go up to infinity and down to -infinity. So it's okay for us to have in here a function value for tangent that is not between -1 and +1. So let's just pick one at random here. Let's pick, I don't know, 3. So let's do inverse tangent of 3. So we're going to do inverse tangent of 3 equals 71.57 degrees. 71.57 degrees. So all we're doing is we're finding the angle whose sine is that, or the angle whose cosine is that, or the angle whose tangent is that. So hopefully that's all I'm going to need with my calculator. Okay, so how are inverses formed? So we remember forming the inverse. All we need to do is just switch the x and the y. So I want to take a look at the sine curve, and we're just going to do all our work with a sine curve for just a moment. Actually, let me go back this way a little bit. And when we draw our sine curve, I'm gonna stick in degrees for the moment. Again, I think most of you think a little easier or a little more clearly in degrees. I'm going to go to -90 here. And so here's our sine curve from 0 to 360. And I'm just going to include down here to back to -90 just because. And the lowest y value for the sine curve, of course, is -1, and the highest is 1 because that's what the range is. Okay, so when we are forming the inverse of this function right here, we're just going to switch the x's and the y's. And so it should make sense to you that the x-axis is really going to be on the y, and the y-axis is really going to be on the x. So we're just going to really switch the x-axis and the y-axis. And so if we were to draw the inverse of this, I'm not going to go through the whole long process of taking individual points and flipping them so that we can actually find the graph. We would see that the graph looks something like this. It just winds its way up the y-axis and down this way also. So this is what the arc sine graph looks like, sort of. So I ask first the question before we continue on observing what this is all about. And so again, all we did is we just flip this, the x and the y, so that all this curve just ended up going up the y-axis instead of across the x-axis. So is this a function? And clearly it's not, because it doesn't pass the vertical line test. So the question is, how do we make it into a function? Well, if we were to just get rid of some portion of this, let's say everything above the red line right there and everything below the red line right there, we would have a little piece of the curve that passes the vertical line test in all locations. So that's what we're going to do. So the graph of the arcsine function the graph of arcsine is made into a function by just limiting its domain and range. So that's the way we fix the problem. So we limit domain and range to ensure function, because we want to make sure that we're working with a function here. Okay, so let's take a look at what this is right here. And again, we are switching the x-axis and the y-axis. So along here, we should be going from -1 to +1. And up here, we should be going 90, 180, etc., and all the way down to -90, and so on. And so we can see that the domain for this function between the red marks here is from -1 to +1, and the range is from -90 degrees to +90 degrees. So let's sketch that right in here. So this is going to be our graph of the arcsine function. So it's going to look like this. So in a lot of ways it looks a little bit like x cubed. There's 1, and here's 90, and here's -90 degrees. So as we already talked about, the domain for this guy here is -1 is less than x, less than or equal to x is less than or equal to 1. And the range is going to be -90 is less than or equal to y is less than or equal to 90. So it's a limited domain. So now I want to go back just a moment to where we were over here. So let's talk about what angle has a sine that's 0.5. Well, if we take a look at this graph right here, and we go to 0.5 right here, we can see that there are two angles. And if we keep this graph going on forever, there's going to be an infinite number of angles whose sine is 0.5. But the calculator, when we used the calculator, only gave us one value. And that is explained right down here. Because for 0.5 being like right here, there is only one value. It's right there, 30 degrees. So this ensures that we're only going to get one value anytime we use the arcsine or arccosine or arctangent, in this case arcsine. So we only get one value, even though there are an infinite number of values, because we limited the domain and range. Okay. So, as I said, that explains why the calculator only gives us one value, because we limited, or the definition of that function is limited in its domain and range. Okay, so let's make sure we have the other three major functions, and we'll go on to the other ones later. So we're going to do the arccosine function. The arccosine function looks obviously a lot like the arcsine function, only it is entirely above the x-axis. So we can see we're going to have 180 here, 90 here, 1 here, -1 here. And so if we're just using this graph right here, we can ask ourselves, all right, well, because here we're choosing our function value, and here is where we get our angle. So the cosine of what angle has a value of 0? Well, go up to here and we find 90. The cosine of what angle has a value of 1? Well, 1's right here. What's the angle on the y-axis? 0 degrees. The cosine of what angle is 0.5? Well, here's 0.5, and we go up right here. We go across here, And if I draw my graph a little bit better, we'd see that that's 60 degrees. So again, your calculator is going to do most of the work, and then you're also going to have some reference triangles to work with that we've worked with before. Okay, so let's do the domain of this guy right here. So the domain is obviously from -1 to 1, just like it was with the other function. So the domain is -1 less than or equal to x less than or equal to 1. And the range is going to go from 0 degrees up to 180 degrees. And again, I've included degrees here, but of course we can always think of this in terms of radians by just changing this to pi, 0 to pi. All right, so we know the arctangent, or the tangent function, has asymptotes, and so no big surprise, the arctan function also has asymptotes. And so I'm going to put in two places where we have our asymptotes here, -90 degrees. And that shouldn't be surprising because we have asymptotes at 90 degrees, and if we went back a little bit, we'd have -90 degrees. And we know we go right along the asymptote, we go through the origin, and we head towards the other asymptote. And that is what our arctan graph looks like. And so the domain for this guy here, as you can plainly tell, goes from all the way to the left to all the way to the right. So the domain is going to be all real numbers, just like the range was when we had it like that, sort of. And the range for this guy here is going to be from -90 to 90. So -90 less than or equal to y less than or equal to 90. Just like it is, oh, not equal to. Just like it is, or very similar to the sine curve. Okay, so these are what the graphs look like. These are the definitions, including their domain and range, because it's important to understand, again, how it is that your calculator is getting these values and how these functions are defined. So for the cosine function, again, we're only going to have one function value for every x value. So if we chose, for example, +1/2, we would get 60 degrees. If we choose -1/2, we're going to get not 60 degrees, but rather 120 degrees. So let's see if we can do some of these problems right here. All right, so this is 1/2 right here. So what we're asking then is the cosine of what angle is 1/2? And so, of course, you should remember this from your little reference triangle right here, hopefully. You should remember 1, 2, √3, and 30 degrees in there, 60 degrees down there. So the cosine of what angle is 1/2? So let's take a look at these angles right here. So we got 30, and let's do the cosine of that. So that's going to be √3/2. That's not 1/2. Let's try 60. Cosine is adjacent over hypotenuse. That's 1/2. So the angle whose cosine is 1/2 is 60 degrees. And here's where all that memory and memorization comes in to play, right here, with these problems and other problems. We're going to be solving equations soon, and we're going to need this information. So that's why I keep having you practice on thatquiz.org, so you can learn this stuff and make it more permanent and quicker. All right, so then we go back here and we do the next problem, and we ask the sine of what angle has a value of 0? Well, of course, we remember the sine curve graph from way back in the day. So there we are right there. So the angle is 0 when the sine is 0. So 0 degrees. And the arctangent of 1. So hopefully you remember that with our other special triangle right here. We have 45 degrees, 45 degrees, 1, 1, √2. So the tangent of what angle is 1? Well, 1/1 is 1. So then the angle must be 45 degrees. And again, what I'm trying to do here is, with thatquiz.org, is associate these things for you or with you. So we know that the tangent of 45 is 1. Or what angle has a tangent that's 1? 45 degrees. Okay, so let us do a few more of these that are a little less a little less obvious. So root 2 over 2, hopefully you remember from your practice that the sine of some angle is root 2 over 2. So we want to know what that angle is. So hopefully you're searching through your memory and you're going to come up with 45 degrees. 45 degrees. Hopefully you came up with that. So I'm going to pause right here, and you should do your push-ups right here. I would like you to do this problem right here. What angle has a tangent that's root 3? So pause the video, take a moment, figure it out. Hopefully not too long. All right, well, hopefully you remembered from all of your practice that this is going to be 60 degrees. And again, if we go back to our little triangle that I have over here, right here, and we're talking about the tangent. So here we have root 3, here we have 1. So root 3 over 1 is going to be the tangent of root 3. So what angle are we talking about? 60 degrees. Okay, so here's where this is really important in terms of what the domain and range are. So here we're looking at the cosine of what angle is negative root 2 over 2. So let's go back here and look at our cosine here. And so we can see that our cosine graph goes from -1 to 1. Of course, we already knew that. But the y values, the angle measures, go from 0 up to 180. So we want to do negative root 2 over 2. So hopefully you are remembering that when sine and cosine involve root 2 over 2, then we must be involving some sort of 45-degree angle. So negative root 2 over 2, by the way, is about 0.707, so we're going to call that like right about here. And I'm going to draw this straight up to exactly where I want it to be, right there. I drew that straight up and down, and it came out perfectly that it was right exactly between 90 and 180. So this is 135 degrees. That's what we're looking for, because again, that was exactly straight up and down. So the cosine, whose angle is negative, the cosine of what angle is negative root 2 over 2? That angle is 135 degrees. So not only is it important to know your function values, but it's also important to know what the domain and range are by looking at these graphs. It's important to know what the domain and range are so that you're not just getting values that are not realistic and not associated with a function. Okay, so time again for you to do some push-ups. So you're going to do the work right here. So you're going to find the angle whose sine is negative root 2 over 2. So keep in mind what the domain is for sine. If you're going to look back, that's cool. Please do that right now. Pause the video. Okay, so hopefully you remembered that the domain and range for sine are involved in this graph right here. So if we're talking about negative root 2 over 2, that's going to be over here, negative 0.707. So we can see that that's going to be down in this direction right here, and that's negative 45 degrees. So hopefully you came up with negative 45 degrees. All of this is by hand. Okay, almost done. So let's take a look at root 7 squared. And of course we remember from before that square root and squaring are opposite functions. They're inverses of each other. So when we apply a function to its inverse, basically they just cancel each other out because they're opposite operations. So the answer to this, of course, is just 7. Because again, when we apply the function to its inverse, we just cancel both things out. So we just have the 7. So let's go right down to here. So we know that the arctan is the inverse of tangent. So these guys are going to cancel each other out. So the tangent of the arctangent of 10 is just 10. And again, remember, tangent can go up to positive infinity and down to negative infinity. So let's just analyze this a little more closely. So let's work from the inside out. So we're looking for the angle whose tangent is 10. So I don't know what angle that is. Let's say that it's, I don't know, 87 degrees. So now we want the tangent of 87 degrees. Well, the tangent of 87 degrees is 10. So there we are at 10. So Tangent and arctangent just cancel each other off. So there it is, 10. And 2 problems to do, and these are really pretty simple, just kind of definition problems. So we want to write theta as a function of x. So we want to be able to write theta equals something. So we can see that theta is going to be associated with the x and the 5 here, and this is the x is the opposite and the 5 is the adjacent. So this is going to be a tangent thing here. So the angle is going to be associated with tan. And remember, arc means angle. So what angle, that guy right there, what angle has a tangent that is x over 5? And that's all we had to write for that. Because all we're looking for is to write theta in terms of x. Okay, same kind of show right over here. So you need to figure out what function is being involved here, and then just make sure you put an arc in front of it because we're looking for an angle, and then the stuff in terms of x's and other numbers. So please take a moment right now, do this problem, and pause the video. Okay, so hopefully you're able to get the idea that theta is going to be associated with the adjacent and the hypotenuse, and so that is obviously cosine. So we were looking for the angle, remember theta is the angle whose cosine is 3 over x plus 1. And there you have it. Sorry that was a little longer than I anticipated, but that's the way it goes. I'm sure you had a wonderful time. So I'll put up an assignment, and I'll see you on Monday. Have a good weekend. Be safe.